Mathematics Mth 103 here, Mr. Johnny, on this particular course. So we go on with key concepts in set theory, right? First, we look at subsets and supersets, right? Please, you won't mind the notations that I've used for these concepts that we'll be looking at are notes coming up. So I will just find a way to describe. Then I hope you understand, but hopefully the materials will be ready. I'll put them up to the platform where you all can see. So superset or subset and supersets, consider two given sets, A and B. If the set A consists of some or all elements or elements of set B, then A is said to be a subset of B. Again, I'll take that again. That if a set A contains some or all elements of set B, then A is said to be subsets of B. We denote subsets by a set notation. There you have a long C and a dash under it, a long C shape and a dash under it. That's supposed to be notation for subsets. So you have A subset, A is a subset of B. A is a subset of B. The notation again is a long C shape with a dash under it, a line under it. Okay, an underlined C shape. Let me put it that way. So if set A is a subset of B and there is at least one element in set B which is not in A, one element in set B which is not in A, then we say that the set A is a proper subset of B. The set A is a proper subset of B. All right, so there is the notation for proper subset, all right, which is simply a long C, all right. Now A, which indicates that A is a proper subset of B. Now B is also considered superset of A. B is considered superset of A, the other way around. Now, the notation for superset is simply the long C facing the left direction this time around, all right, facing where the B is. Okay, so B is a super subset of A in the other way round, all right. Now we see another concept, power set. The set of all the subsets of a set X is called the power set of set X, right? The power set of set X. Now, the number or the subset that a particular set can form, the subset that a particular set can form is simply known as power set of that particular set. Now, for instance, you have from the screen, you have x1 being equal to A, having elements A, all right? Now, we determine the power set of x1, the power set of x1, that's P into bracket x1 close bracket. Now, this simply tells us how many or the number of sets or subsets that can be found in sets X1, number of subsets that can be found in set X1. Now we have a null set. We have the elements A in set X1, the null set and element A in set 1, set x1. Now we also asked to find the cardinality of the power set of the sets x1, cardinality of the power set of set x1. This simply tells us the number of subsets that can be found in set x1. The number of subsets that can be found in set x1. All right, and which is the null set and the elements A, the set of elements A, giving us two subsets, There's an example, a second example there on the screen, where x2 is supposed to be a subscript 2, x and a subscript 2, that's the right notation for that, where x2 contains elements 1, 2, and 3. X2 contains elements 1, 2, and 3. Now, what is the power set of X2? We have the null set, 1, element 1, element 2, element 3, and sets of 1 and 2, sets of 1 and 3, sets of 2 and 3, and finally sets of 1, 2, and 3. Now, the cardinality of the power set of x2 now gives us the number of subsets that x2 is able to form. The number of subsets that x2 is able to form. If you count closely, you find out that the subsets formed when you have 3 elements of set x2 are 8 subsets. 8 subsets. That tells us that the cardinality of power sets of x2 is simply 8. Now there is an expression or a formula that is used to predict cardinality of a set. Cardinality of the power set of a given set, all right, which is simply 2 raised to the power m. Please mind that that is 2 raised to the power m, not 2m. 2 raised to the power m, where m is simply the number of elements present in the given set in consideration, the number of elements present in the given set in consideration. So in this case, we have 3 elements for set x2. That makes it 2 raised to the power of 3. That gives us 8. All right, we can see that this coincides with the number of subsets when you count literally. It gives 8 subsets. All right, having seen that, we look at universal sets, unit set, and empty set. Universal set, unit set, and empty set. So quickly, the set which contains all the possible elements of sets under consideration, the sets which contains all the possible elements of other sets in consideration is called the universal set. All right. The notation for universal set is the mu symbol, You can see that on the screen, the mu symbol. All right. Now, a set, talking about unit set now, a set that contains only one element is called a unit set, okay? Because it contains just one element, all right? Now, if A contains element X, we say that A is a unit set because it has only one element, a small x, right? Now, we also see that when a set doesn't have an element, okay, we call that an empty set or a null set, right? Denoted by the omega symbol, okay, that's the omega symbol, right? Omega symbol or an empty curly brackets open and close. empty curly brackets, open and closed. All right. Having seen that, we move straight down to finite and infinite sets. Finite and infinite set. Now, when the number of elements in a given set is finite, it means that the set has a definite number of what elements. I repeat that again. When the number of elements in a given set is finite, it means that the number of elements in that set is definite, it is countable, it has an end. All right, not just countable, it has an end. All right, definite. All right, for instance, you say if A contains integer um 1 to 10. All right, integer 1 to 10. All right, we can easily list these integers out 1, 2, 3, 4 to 10. All right, the number of elements in set A is definite. All right, we can easily list them out. But if the number of elements in a particular set is not finite, all right, we call that infinite. It means that this number cannot be exhausted. We cannot exhaust the number of elements in that particular set. Okay, so there's an example here where it says the set A containing all positive integers. The set A containing all positive integers. Now, for instance, this is what infinite. Okay, since we cannot list all the elements in the set A, we cannot list all the elements in the set A, right? Now, the set B contains positive integers greater than 1 but less than 10. All right, this is another example for finite sets, right? Set B containing positive integers greater than 1 or less than 10 is a finite set, okay, because these members can be easily listed, right? We have 1, or sorry, 2, 3, 4, 5, 6, 7, 8, 9. All right, positive integers greater than 1 or less than 10. So we have numbers 1 to 9 being members of that particular set. It is a finite set. It is a finite set. Now for infinite sets that cannot be listed completely, all right, we can simply say that set A, as seen in the first example or illustration, containing elements 1, 2, 3, 4, and we can use dots, 3 dots, okay, to denote continuity of this set, 3 dots to denote continuity of the set, right? Now, we have seen that there is no limit to the number of elements in the set A. The 3 dots indicate that the members of set A continues indefinitely, as I have explained already, right? More concepts in sets. We have equal sets. Equal sets. 2 sets are said to be equal if they contain the same number of sets, all right, and they contain the same kind of elements, the same kind of elements. The order of arrangement of this set might not be important, or it's not important, but what is important is that they contain the same number of sets and also the same kind of set. Like you can also say that equal sets A and B are said to be that A is a subset of B and B is a subset of A. You may want to look at it that way as it is given to you in your material. So now the symbol equality, the equal symbol is used to denote equality of 2 sets. And when 2 sets are not equal, when 2 sets are not equal, the inequality symbol, all right, that's the strike through an equality sign is used to indicate non-equality of 2 sets, For instance, A not equal to B. Okay, when they are not having the same number of or the same kind of sets containing the two sets. Right now we have disjoint sets. Disjoint sets, two sets A and B are said to be disjoint if they have no elements in common. All right, there's no element in set A, for instance, that is found in set B. There's no element in set B that is found in set A. We can also say that set A and B are disjoint if the intersection between these sets are a null set. If the intersection between set A and B is a null set, meaning that there is no intersection between them. There is nothing linking them together, right? Those sets are called disjoint sets. They're called disjoint sets. Okay. Now we further see operations on sets. What are the operations that we can run or can do on set theory? First of all, we see union of sets. Union of sets. The union of sets is the set which contains elements that are either in A or B or both. Okay, simply say the combination of elements present in set A and set B, all right, is said to be the union of set A and B. Mind you that if these elements have, or if these sets have any elements in common, these elements will not be repeated when you are expressing their union. There is an example there given in the material. G, if G contains elements H, E, A, P, H, E, A, P, and H contains elements L, A, K, E, right? Then we say that G union H, G union H gives us H, the elements H, E, A, P, L, and K. H, E, A, P, L, and K. Mind you, A is found in these two sets, but it is not repeated in their union. We have a single A representing that in their union. Also, we see that E is present in the two sets, but we don't represent the two E's in their union. Please note that we move straight down to intersection of two sets. When two sets A and B have elements that are common to the sets, all right, this is the set of elements common between two sets, all right, that gives us the intersection between set A and B, set A and B. Right, there's an example on the material. Please look through. Let R be equal to all positive integers less than 20, less than or equal to 20, and Q equal to all factors of 20. Let Q contain all factors of 20. Now, we see the sets are listed to be 2, 4, 6, 8, 10, 12, 16, 18, and 20. And that for Q listed to be 1, 2, 4, 5, 10, and 20. These are factors of 20. Now, what are the elements or members that are common between these two sets? We have R intersection Q. R intersection Q, giving us what? 2, 4, 10, and 20. Now, I did not mention the notation for union. Sorry, I didn't mention notation. So, notation for union is simply a U like symbol, U like symbol, all right, or like a cup like symbol, all right, with the downwards curved, right? And the notation for intersection is simply the upside down of that symbol for the union of two sets. All right, simply put, like an N shape kind of symbol for intersection. Complement of sets. Now, if a set A is a subset of a universal set mu, set A is a subset of a universal set mu. Complement of A or set A is a set of members of the universal set not found in set A. All right. Complement of set A is a set of members of the universal set not found in set A. All right. Complement is also noted as prime. So it's a complement of prime is denoted by an apostrophe sign. All right. As a superscript of the set given or in consideration, right? So we'll go into cardinality of sets. We talked briefly on that. Cardinality is simply the number of elements contained in a set. The number of elements contained in a given set. So if, for instance, a set A contains elements A, M, B, D, H, all right, we say that the cardinality of set A is 5. The cardinality of set A is 5. All right. This class is supposed to run 40 minutes because of the basic package for this platform. All right. The class is running out. Quickly, cardinality is denoted by an N. Okay, then the set in question is next we look at Venn diagrams. These are pictorial representation of sets, all right? Operations of intersection, union, and complements, all right, of set can be demonstrated using Venn diagrams. All right, I'd like you to go through the materials for this topic. We also have inequality to look at after this topic, but the time schedule would not permit us. Okay. Okay. Oh, my diagrams are not coming up. My diagrams for Venn diagrams are not coming up. Okay. There are tutorial questions which I'd like to solve with you on set theory. Kindly go through the materials to see these questions. I hope to treat some of these questions in our next class as we go on in the course Engineering Mathematics MCH 103, right? We see inequality, and the basic rule for inequality. Oh, my symbols are not coming up. Okay, basic rule for inequality. We have supposedly number one rule that if A is greater than B, if A is greater than B, and such that C is greater than 0, such that C is greater than 0, all right, then if you add C to A on the left-hand side and C to A on the right-hand side, okay, the signs still remain the same. A plus C is still greater than B plus C. All right. Likewise, if you have A less than B, please take note, the signs are not coming up on the Zoom platform, but I hope you follow me. If you have A is less than B, such that C is greater than 0, all right, then if you subtract, okay, yeah, if you add, all right, A plus C is still less than B plus C. A plus C is still less than B plus C. So it's suffice to say that if that we can add the same constants to both sides of an inequality. It doesn't change the sense of or direction of the inequality symbol, right? That's for one. Secondly, you have that you can subtract the same constants, all right, from both sides of an inequality. You can subtract the same constant for both sides of an inequality. Okay, that's for rule 2. Okay, then rule 3. We have that if A is greater than B, all right, and then we have a C that is greater than 0, all right, we can multiply C on both sides of the equation and still have the same sense of inequality, Note that, okay, A greater than B, and you have AC will still be greater than BC. AC will still be greater than BC, all right, provided C is greater than 0, all right, and also A divided by C will still be greater than B divided by C, all right, provided still that C is greater than 0, all right. Please bear up, my notations are not coming up on the Zoom platform. Now, when you have a C, all right, A greater than B, and you have a C that is less than 0, meaning that C is a negative integer. C is negative integer. So multiplying A and C, okay, and B and C will change the sign, will change the sense of the inequality. All right, the sign of inequality will be reversed because you are using what? A negative integer to multiply on both sides of the inequality. Please note that likewise, when you do division, on both sides of an inequality with a negative integer, all right? So if both sides of an inequality are multiplied or divided by the same negative number, the sign of the inequality is reversed. The sign of the inequality is reversed. So please take note of that. We have 3 minutes left. Now we see linear inequality in one variable. Linear inequality in one variable. So the basic thing you should understand that is that the basic principle applied in solving linear equations, right? A lot of us have done a lot of on linear equations, solving equations. This principle that you apply in solving equations also apply here in solving linear inequalities. In solving linear inequalities in one variable, with just the slight exception of rules on multiplication and division by negative numbers, all right, which reverses the sense of the inequality. That's just a slight slight difference. Okay, so we have examples. Oh, my examples are not coming up to, they're not coming up. They're not coming up. Let me see if I can pick. Okay, the examples we have supposedly are for you to find the solution sets of the following inequalities. To find the solution set of the following inequalities. Number one, we have 2x plus 1 less than x plus 5. 2x plus 1 less than x plus 5, right? Then, secondly, we have 1/3 x plus 2 greater than or equal to 1/2x plus 1. 1/3 x plus 2 greater than or equal to 1 over 2x plus 1. Then thirdly, we have that you find the solution set of the inequality 3x minus 2 greater than or equal to 1 over 2x plus 3. 3x minus 2 greater than or equal to 1 over 2x plus 3. I'd like to draw up to close the class here, and hopefully I'll do better in the slides presentation. I'm going to see how I can ensure this omissions doesn't take place in the next class, right? This is Mr. Johnny once again. I wish you the best.